This video is going to be me going through the notes for rates of change. I'm not going to read the notes to you. You can pause the video and read the notes yourself, or you can download a blank copy of the notes, read it from that PDF file. I don't want to read it to you. That's not fun for anybody. Not fun for me. Not fun for you. Not going to do it. Right? So pause the video if you want to read. But generally, the stuff at the very beginning seems fairly introductory. I'm not going to be too worried about it. Generally, this whole concept of a rate of change is just another way of saying slope. And there's two different types of slopes that we're going to be interested in. One of them we're only mildly interested in. The other one we're very much interested in. Right? And kind of the goal, the one that we care the most about, is the slope of a tangent line. The slope of a line that only touches a function at one point. But, Mr. Bell, how do you find the slope when you only know one point? Well, that's what derivatives do for you. That's like the first half of calculus, is finding out the slope of a tangent line, which is the same thing as the instantaneous rate of change, which is the same thing as the derivative, right? We're going to put the derivative word on it more towards the end of this lesson, and next time. Today, we're going to call it the instantaneous rate of change, or the slope of the tangent line. But in order to get there, right, the slope of a tangent, the slope with only one point, we are going to start with something we know for surezies we can do, which is the slope of a secant line. That's an average rate of change. That's the slope between 2 points of a function. Right, so that's kind of the goal. We're gonna eventually want to get to the instantaneous rate of change, the slope of the tangent, the derivative, but we're gonna start with the average rate of change, which is the slope of the secant. So let's go for it. Again, you can read that on your own. I do not want to read it to you. It says, here's a scatter plot. Here's some points for the scatter plot graphed, yada, yada, yada. Then they go ahead and they calculate that average change in temperature over, looks like, the first 15 days. Great. Okay, cool. You know how to do the slope between 2 points. I think on the next page, it's just going to break down and kind of walk you through with some nice fancy pictures. A couple more rates of change, like here on this first one, they think they did the days 1 through 15, and then I think on this next one they're doing, right, it's kind of weird, this actually goes for the figure 4.3, that actually goes from the previous page. That's okay, right, but you know how to find the secant slope, the slope between 2 points. It's just straight up your slope formula from Algebra 1, which is down at the bottom of this page. We'll get just in a second. Here's the second example. You know, if you pick two different points, the slope between those two different points is going to be different, right? The slope between 1 and 15 is different than the slope between 16 and 19. So the interval of your x values, right, the part of the graph that you're looking at, that's going to change what your average rate of change, your secant slope, is. Duh, that makes sense. Okay, speaking of average rate of change, here's your formula, right? y2 minus y1 over x2 minus x1. That's just straight up slope, but specifically average rate of change is your slope of the secant line. And remember, your secant line, if you don't remember from geometry, I'm about to tell you anyways, a secant line is a line that's going to touch your graph twice. So there's going to be two distinctly different points, and you know how to do the slope when you have 2 points. That's great. That's what we're starting with today. Eventually, we're going to care more about the slope of a tangent line. And how do I find the slope when I only know 1 point? Well, that's what we're getting towards, right? Here again is another picture just representing that average rate of change. Slope of the secant line. If you have 2 points, straight up do the slope formula with them. All right, let's actually do some math, right? Enough talk. Let's do it. 4 minutes, what a waste. Let's do some math. The graph in figure 4.5 below, okay, represents the number of meters an object is above the ground after t seconds have elapsed. Find the average rate of change between these 2 points. Great. Okay, so find the slope. So it says find the average rate of change, and it specifically said between time equals 3 and time equals 8. Very nice. So let us use our slope form. Remember, your slope is just rise over run. Your change in y over your change in x. Your change in distance. Here your units are going to be in meters over your change in time. So this is going to be an average speed. So let us go for it. And it really doesn't matter if you do the slope from P1 to P2 or if you do the slope from P2 to P1. As long as you get the order consistent with the subtraction, it doesn't matter. So which one you want to call x1, y1, and then which one you want to call x2, y2, that doesn't matter. You could flip them, it doesn't matter. As long as if you use this for y2, then you had better use this for x2, right? Or if you use this for y2, then you need to make sure you use this for x2, right? Whatever you're doing, just make sure you're consistent. Let's just call this one x1, y1. We'll call this one x2, y2. But if you did the slope in reverse, the negatives will cancel. You'll end up with the same thing. So let's go for it. y2 minus y1. So I've got 18 minus 25 over x2 minus x1. We know how to find the slope. It looks like here that difference on the top is -7. The difference on the bottom, that definitely kind of messed up. I started doing too much. The x2 should have been, or the x1 was 3. See, silly Mr. Bell started to do the math in his head and then wrote it too fast. That number should have been 3, which means the answer ends up being 5. I tried to just put the 5 right there. Shame, 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 Mr. Bell. That's okay, I caught it. All right, here we go. Let's go ahead and convert it. You can get it to a decimal if you want. I don't really care. It's -1.4. Definitely, though, we're concerned about units. So how I would write them, it would be meters per second. All right, if you want the decimal, that's fine. Or if you like the IB notation, right, here we go, -7 over 5 meters seconds to the negative first power, right? This is all the same thing. I don't care. You can use the fraction or you can use, since this is a nice decimal, I don't care if you use the decimal. But I know IB, they kind of like your meters and then seconds to the negative first power. All of those equally valid. You wouldn't get counted off for any of them. So whatever makes you feel all warm and fuzzy, you just do it that way, right? Okay, first one, pretty easy, right? Average rate of change is just the slope between 2 points. Super easy. Always watch out for your units. If you don't put your units, very good chance that you're going to lose a point or 2 on your answer. So if you want to, you can always just circle the units in your question. That way you make sure, hey, when I have my answer, do I have the correct units? Here I need units for the distance over units for the time. Pretty simple. Okay, let's look at this next one. Right, and kind of the interpretation. Sometimes you get these questions that say, okay, interpret what this answer means. This answer right here, it kind of is telling you between the 3rd and the 8th second, the object was falling at an average rate of 1.4 meters per second, right? Really, this is an average velocity. Since it's negative, it's a velocity. An average speed would be positive, right? But velocity, that negative just indicates you're going in the negative y direction, so you're going down. So the average speed would be 1.4 and it's going down, or you could say it's falling at a rate of 1.4 meters per second. That's the rate of change, that how your height is changing with respect to time, right? So between time equals 3 seconds and time equals 8 seconds, the object was falling at an average rate of 1.4 meters per second. It's not always going that same speed. We know gravity causes things to accelerate. So sometimes it's going to go faster than the average. Sometimes right when it starts, it's going slower than the average. But the average over an interval is still useful. But we know the instantaneous value for all of those millions of nanoseconds in between 3 and 8. We know that instantaneous value isn't always going to match the average. The average just tells me, hey, over an interval, what's the average? So keep that in mind. All right, let us go through and let's shift and let's do 4.3. The number of annual layoff events. Ooh, this is an ominous question. The number of annual layoff events that occurred in the U.S. from 96 to 2001 can be modeled by this function f of x. What an ugly function. Okay, where it gives me the domain restriction 1 to 6. So it looks like here, this is going to be x equals 1. This is going to be x equals 6. Very nice. Where x is the number of years since 95. Okay, cool. And f is the number of thousands of events. Oh my gosh. Okay, so if we get an answer that's 4, remember, it's really 4,000 events. So just always be careful for your units. Find the average rate of change in the layoff events from 96 to 2001. Okay, great. So it's average rate of change, so just your slope, average rate of change, and that's going to be from time equals 1 to 6. Very nice how it gave us the very nice t-values translated for us. We can also see it looks like this graph is already labeled. If you didn't have the graph, of course, you would just type this function in, and then you would just evaluate that function. I'm going to go ahead and do it. I don't necessarily trust that the values in the table are correct or in the graph are correct. They probably are, but let's check it. I'm going to type this sucker in, and then let's see if we actually generate something consistent. Go away, pop-up. It always comes up, no matter how many times I hit 1. 0.066x. I probably don't have to read it to you. Sorry, that's annoying. Okay, lovely. Let's go check it. Let's see if this point, if I plug in 1, let's see if it actually does give me the 5.746. Cool. Let's try it. Vars, scroll to the right, y vars. We're in function mode. Bam. I have that function typed into y1, and I'm going to tell it to evaluate at 1. Oh, it looks different. How about that? So that data in the table, or that data in the, let me make sure I have it typed in correctly, 0.0066x to the 4th. Oh, what the heck? Okay, yeah, I definitely have this asterisk right here. I don't know why that's there. Okay, let's see, then it should be minus. I had a negative sign. Oh my gosh, what was I doing? So hopefully you caught that when I was typing it in, and you'd be like watching this video, be like, Mr. Bell, I know it's going to be wrong. You're an idiot. That's okay. Went back, fixed it. I think that looks okay. Minus 0.8. Make sure you do the minus sign, not the negative sign. Minus, that looks good. Plus, cool. Okay, let's try this again. Okay, if you didn't get those instructions, how you can evaluate a function, obviously you can go to your table and then you can scroll. It looks like I have it typed in, and that is going to match. How lovely. You can go to your table and you can scroll. That's great. But how you can also evaluate a function on your home screen, you hit the vars, that stands for variables. Then you need to scroll to the right, y variables. This is going to be based on what mode your calculator is in, and for us, we're always going to be in function mode. And then if you have an equation typed into y5, then you would need to scroll to y5. But here I have my equation in y1. And then I'm going to go snag that algorithm that's currently stored, right? That function that's currently stored in y1. Then I'm going to tell it to evaluate. And look, that matches. How lovely. Okay, so let us go through and do it. Always write supporting work for your IB questions, right? Always show work. Make sure you're not going to miss any points. So we have f of 6 minus f of 1 over 6 minus 1. As long as you had this, then you could jump to the answer. That would be fine. If you wanted to actually write some more, that would be okay. But as long as you have what formula you're using and then you have the answer, that would be fine. I usually like to show here's the formula, here's the values getting plugged into the formula, and then you can jump to the answer. So this one we had 5.746. And then let's go evaluate it. Now you can do vars, y vars, y1, and then I could tell it to evaluate at 6. That would be fine. Or shortcut, if you've got an 84, you can just scroll up, click enter. That means, hey, go snag the same algorithm, and then I'm just going to change it so that it evaluates at 6, right? If you know how to use a calculator, it can save you quite a bit of time. 7.316. How lovely. This picture actually does match the values. Every once in a while, I do something that makes sense. And then let's do the subtraction. So let's do this minus this, and then we can divide it by 5. How lovely. So it looks like this average rate of change is going to be 0.314. Remember the general rule of thumb for your answers, it should be 3 sig figs unless otherwise indicated. So this one you would want to leave it as 0.314. Do not round it to 0.3. Do not round it to 0.31 unless it tells you otherwise. And don't forget your units. That's 0.314 thousands of layoff events per year. Right, so 314 layoff events per year. Right, so again, the interpretation of this, it would be the number of layoff events was increasing because it's a positive rate. Previously, we had a negative, so that means it was decreasing, right? The height was, the ball was falling, or the rock was falling, whatever it was. Here, since it's positive, we know it's increasing. So here, the number of layoff events was increasing at a rate of 0.314 thousand. Or if you don't like 0.314 thousand, you could just say 314. But it's increasing at that 0.314 thousand events per year from 1996 to 2001, right? And that's on average. It doesn't mean every single year they laid off 314 people. That just means on average. Some years they may have been nicer, like maybe they only laid off 200 people. Maybe some years they just laid the hammer and they just fired 500 people. Who knows, right? But on average, 314 people got laid off, or there was layoff events. Alrighty. Let's look at this next one. And now it's got some stuff for you. And that's cool. You can pause the video, you can read this, but really I kind of like to talk about this instantaneous rate of change in my own specific way. I think the way I explain it hopefully makes sense. Let me flip it over. Yeah, it kind of is just going to go rambling on. I'm going to kind of explain where this formula comes from. But I'm going to pause the video, then I'm going to flip it over. I'm going to get some blank paper. Again, you guys can read all this stuff. I'm not going to read it to you, but you can read it. And then let's see on the next page. Oops, trying to move it. Sorry, everything on my screen is backwards. So I move it to the left and it goes right. And then you guys can again pause it and you can read this. But I'm going to, on a separate sheet of paper, I'm going to kind of create this for us in a slightly different manner. All right, so hold tight. Poof, as if by magic, right? I just drew this sample function. My drawing skills are limited, so I typically go back to the wheelhouse of a very easy kind of parabolic shape function. It really doesn't matter. You could do any type of a graph, doesn't matter. But here I have just a sample graph. I labeled it as f of x. I've got one point. I call this arbitrary point x. And so if I plug that point into the function, I'm going to have a corresponding y value, and that y value we'll call f of x, right? Or y, but f of x for now. Okay, now I've also got a second point on this graph. And really, I want to call the gap in between those 2 points. I'm going to call the gap h, right? So segment addition time, going back to some geometry. If that distance is x, and if this distance is h, then if I wanted to find an expression for the second x value, it would be x plus h, right? So here, this second x value, x plus h, and then it goes up, hits the function. So then here, this second y value would be f of x plus h. Now, I know if I have these 2 points, they're arbitrary now, that's okay. But I know if I have these 2 points, I could find the secant slope between them. Right? And right here you'd have your secant line, and you could find the slope of that secant line. That's great. Here's how you would do it, right? Your secant slope. See if I'm still on the screen. I think so. Cool. It's just your change in rise, change in y over your change in your x, rise over the run. So you'd have y2 minus y1 minus f of x over x2 minus x1. Okay, now let's look at the denominator really quickly, because something's going to happen. In the denominator, you have x plus h minus x. So those x's, they're going to cancel, right? So you're never really going to see them again. Typically, what you're going to see in the denominator is just the h, right? But here we go. I've done the secant slope. I did the slope formula connecting those 2 points, y2 minus y1 over x2 minus x1. The x is canceled. This right here, that's called your difference quotient, by the way. Difference quotient. Now, in a regular year, coming from pre-AP or coming from your advanced pre-cal, you would have seen this a couple of times, specifically at the end of the year. I don't know if you guys did last year. That's okay. But this is your difference quotient. It's the slope between 2 arbitrary points, right? You have some first point, x. You have some second point, x plus h. The gap in between them is h, right? So I've got some arbitrary slope between 2 arbitrary points. That's great. Secant slope, average rate of change, cool beans. But I don't want the average rate of change. I don't want the slope of the secant. I don't want the slope with 2 points. What I really want in a perfect world, right, is how can I find the slope of this tangent? How could I find the slope of the graph that is only going to touch the equation, or is only going to touch the function in one spot, right? So here I'm kind of drawing myself a little tangent line. And then I want to know how to find the slope of that tangent line, right? And that is what the instantaneous rate of change, or that is what the slope of the tangent, and that is what the derivative is going to be, right? The rate of change, not over an interval, not with 2 points, but the rate of change instantaneously with just 1 point, right? Now, in order to find the slope of the tangent line, aka the derivative, aka the instantaneous rate of change, we're going to have to take something and do something to this secant slope, right? The secant slope is between 2 points. What we're going to want to do is, instead of having 2 points, we're going to try to compress them, and then we're going to try to squeeze those 2 points together, right? And how we're going to do that is through a limit, right? So here we go. The tangent slope, am I on the screen? Kind of, sort of, just barely. Awesome. So what we're going to do is take my secant slope, f of x plus h minus f of x over h. Remember, that right there is your secant slope between 2 arbitrary points. But what we're going to do is take a limit as h goes to 0. Remember last time we talked about limits. This limit is going to turn that gap. Remember, h is the gap in between the two. And as that gap gets closer and closer and closer to 0, those 2 points get closer and closer and closer together. And then eventually, as that gets infinitely close to 0, you're going to compress those 2 points into one. And this limit process shrinks the secant into the tangent. Again, secant line, secant slope, tangent line. The limit process is important. Without the limit, without shrinking the size between those 2 points down to 0, you have 2 points, which is an average rate, which is a secant slope. This limit process is how you go through and how you turn the secant 2 points into the tangent, just 1. So this is your definition for a derivative, and you'll see that written right here. You have your limit as h is going to 0, f of x plus h minus f of x over h. Remember, that's your secant slope between your 2 arbitrary points, but then that limit shrinks the gap down to 0, compresses the 2 into 1. That's your slope of the tangent, and then that's your derivative. So this f prime notation, that is what we're going to use to indicate the derivative, right? Really nice. Instantaneous rate of change, derivative, slope of the tangent. Those are all synonyms. They mean the same thing. And how we're going to find it is through this difference quotient and limit process. Now, this can be a little bit time consuming, but bear with me. We're not going to have to do this every single time we have a limit. We're only going to have to do this for about 48 or 96 hours until next time, because we are going to get the shortcut rules, and those shortcut rules are going to make taking a derivative very, very, very fast and very, very, very easy. Right, so that's nice, but it's important that you kind of suffer through the limit process so that you understand how impactful and how incredibly wonderful those shortcut rules are. Right, now let's go for it. I don't have enough room right here to actually do this work, so I'm going to pull out another piece of paper, and let's just do it there. But we've got Janice with her jewelry store. Okay, cool, Janice. You found that your profit you make each day can be modeled by this function, p of x. Great. Where p is the number of days after Christmas, after December 25th, and p is the profit measured in hundreds of dollars. Find the instantaneous rate of change in the profit. So find the instantaneous rate of change for this p function the 3rd day after Christmas, and then the 6th day after Christmas. Okay, cool. Let us go through and do it. So this is going to be 2 parts. We're going to have a limit process, right? We're going to use this formula, and we're going to use time equals 3. And then we're going to have the limit process where time equals 6. Okay, let's go for it. I'm going to copy that function, p of x, negative 4x squared plus 40x minus 60. Cool, and we're going to do part 8, where the x is 3. And then I'm going to write it up here, the part B, where x is 6. And I'm going to move that off to the side. Okay, let's go for it. This video is going to be fairly long. That's okay. Hopefully it's useful, laying the foundation for differential calculus, which we're going to be doing all the rest of the year. Cool. Let's do it. We got the limit as h is approaching 0. Now you need, right, here's your formula. Limit as h is approaching 0, you need f of x plus h minus f of x over h. So what you would do is you would take that function and you would plug in x plus h. So anywhere you see an x, you're going to plug in x plus h. Then you're going to subtract that whole original function. So here we go. Negative 4x plus h squared plus 40 x plus h minus 60. Right? All of this stuff right here, that's your f of x plus h. And then you have your original function, just copy it. 4x squared plus 40x minus 60. Please make sure you either put brackets or you put parentheses around your original function. If you don't put your parentheses, you're probably going to forget to distribute the negative, right? Be careful. Then all of that is over h. Okay, so we need to do some algebra. If you try to plug it in right now, you're going to get 0 over 0. That's an issue. But if we just do the algebra, some magic is going to happen. Some h's are going to reduce. Some non-h terms are going to cancel. We're going to get an answer. We got to do all the algebra first. So let's just multiply all this stuff out, and then we'll distribute the negative, and we'll see how it's going to shake out. Until you plug in the h's to zeros, right? Until you evaluate this limit, you need to continue writing that limit notation. I know it's annoying. Suck it up. Okay, let's go ahead and distribute. Now that would be x squared plus 2xh plus h squared. And then I'm going to distribute the 4 also. So I have negative 4 x squared. Then you'd have, I think, a negative 8 xh minus 4h squared. Then we have plus 40x plus 40h minus 60. Distribute the negative to all of those terms. So plus 4x squared minus 40x plus 60. Okay, wonderful. Now let's go ahead and look and see if there's any terms that cancel, and there should, right? Anytime you're doing this difference quotient, eventually what you're going to want is to get this h out of the denominator. But you can't divide by h if some of the terms in the top don't have h's, right? If every single term in the numerator had an h, then you could reduce it by h and you'd be good to go. But there are some non-h terms in here. Luckily, every single time that you do a difference quotient, the non-h terms should always and will always cancel as long as you've done all the algebra right. Like here, that one has its counterpart over there to cancel out with. And then that one's got an h, so it's going to stay. That one's got an h, so it's going to stay. Any term that does have an h should not cancel. But then any term that doesn't needs to have its negative counterpart, and then they're going to reduce. So that one's going to stay, that one's going to go, and it has its partner, right? So all of the non-h terms should always and will always cancel, as long as you've done the algebra correct. Let's regroup and let's see everything we have left. Negative 8xh minus 4h squared plus 40h, everything else canceled. Wonderful. Now, out of the stuff that's left, everything has at least one h. So now you're going to be able, and you could do this 2 different ways. If you want, from the numerator, you could just factor out one h to the front and then cancel that one h with the one on the bottom. I don't typically waste the time to do that, but conceptually, that's what we're going to accomplish. Typically, what I do, though, is I just think, hey, I'm going to cancel one h from the denominator. That means every single term in the numerator also has to be reduced by 1h. Factor it out, cancel it in the front if you want, or just make sure you reduce every term in the top by 1h. And let's see what we got left over. Negative 8x minus 4h plus, come on, pencil, plus 40. And then finally, we got that h out of the denominator. Now I can evaluate the limit. That thing is going to get plugged in as 0. So here I end up getting negative 8x plus 40. And that is what we would call p prime. That is your derivative function. That equation is going to be how we can find the instantaneous rate, the slope of the tangent line, at any given value of x, right? This limit process, kind of nice. It's gonna give you that derivative formula. So now all we have to do, right? We wanted the instantaneous rate at time equals 3. So then I just have to plug it in. Therefore, the little 3 dots means therefore p prime of 3. You have negative 8 times 3 plus 40. Oops, I don't know why I need a parentheses there, which I don't. Let's see, 40 minus 24 should be 16. So we've got 16, and then your units would be $100. So I'm just going to say the profit. You can either put the units, and it would be $100 per, I think the units for time or day, so it's $1,600 per day, or if we wanted to write out a statement for it, you could. The profit is increasing. Remember, increasing because that value for the derivative was positive. The profit is increasing at a rate of, come on, pencil, stop it, $1,600 per day on the third day after December 25th, after Christmas, right? If the question didn't ask you to write out an explanation, you don't have to, right? Just make sure you have that, or you could write it like this. That's fine. But if it did ever ask you to write out or explain or interpret each answer, which I guess this one did, it says and interpret each answer. So there's your interpretation right there. Now, what's nice is that the part B is now super quick. We've already done all of the limit work. All we have to do for part B is instead of plugging in 3, all I have to do is plug in 6. So here we go. P prime of 6, you can have negative 8 times 6 plus 40, negative 48 plus 40. It looks like that's negative 8, and again, it would be $100 per day. And then our explanation, we could say, let's see if I'm on the screen, kind of, sort of. The profit is decreasing at a rate of $800 per day on the 6th day after Christmas, after December 25th. Right? The profit isn't always decreasing at this rate, or the profit wasn't always increasing at this rate, right? It's only going up by that specific amount at that specific day, and it's only going down by this at this specific day, right? It could happen to hit that same rate at a different day, but we don't necessarily know. So you always just make sure you specify, hey, here's what the rate was, and here's the time value that it was for.